This is the final chapter in our module dealing with capillary evaporites. I want to focus on the origin of the brines feeding sabkha and anhydrite growth in the coastal sabkhas of the UAE, but more broadly in terms of how does capillary evaporation work in both continental and marine-fed settings. So we want to consider, is the main solute brine source marine or is it a continental brine? Are the brines moving through the sabkha by rising from the water table below the per ascendum model, or are most of the brines supplied from brine sheets which periodically flood the surface of the sabkha? And we'll also consider the hydrological implications in terms of the inherent brine volumes from various sources and the solute volume limitations in those capillary salt growth zones within the capillary zone, tying it back to the notion of, are these prograde or retrograde salts forming in that zone of capillary evaporation? Before we do that, let's remind ourselves of the general principles that we established right at the very beginning of this discussion of capillary zone evaporites. We made the general overarching observation across all evaporite settings, be they capillary evaporites, subaqueous, that evaporites are hydrogeochemical sediments whereby the hydrology will control the depositional and the diagenetic textures, and the brine geochemistry will control the depositional and diagenetic mineralogies. If we're in a saline pan environment where we have ephemeral brine sheets, those textural characteristics will alternate between subaqueous and subaerial, whereas in sabkha and mudflat capillary evaporites, we're seeing evaporite salts that are a response to the processes of capillary evaporation. Let's now relate this back to what we see in a coastal sabkha as exemplified by the sabkhas forming along the Gulf margin in the UAE, especially in the Emirate of Abu Dhabi. In the previous section we see in the idealized section a stack of peritidal sediments passing from subtidal, intertidal to supratidal. We sometimes call this the holy trilogy that we see preserved in a prograding tidal succession. But we noted there are some lateral discontinuities in the facies belts. They're not purely railway tracks marching off into the basin. We do see differentiation into differing styles of aquifer distribution within any marine sabkha. They tend to be obscured by the presence of that very flat overlying erosional surface called a Stokes surface, which flattens the top of all coastal sabkha and, for that matter, all inland continental sabkha settings. In the coastal sabkhas of Abu Dhabi, we noted that in the capillary zone, we tend to see nodular and enterolytic anhydrite forming above the water table. And that anhydrite may convert back to gypsum, and it can go back to anhydrite in that zone above the water table. However, in the zone below the water table, which is roughly the level of that thin red line in the diagram on the right, we see gypsum, typically birdbeak or lenticular gypsum as individual crystals or clusters or rosettes of gypsum forming below the water table. The intertidal sediments are characterized by lamination, typically microbial laminites or pustular matte textures. Below that, we have the subtidal restricted lagoon. And most importantly, in terms of recognizing capillary evaporite distributions, we see these systems capped by that Stokes surface, that erosional surface, which defines the uppermost portion of a sabkha sequence. But let's go back now and look more specifically at the question I asked in that previous discussion, and that is when we look at the anhydrite distribution, why is there so much anhydrite immediately above the water table? Remember back to Owen's Lake, most intense evaporation occurs directly below the Stokes surface, as we saw in the Owen's Lakes barometer profiles. But here in Abu Dhabi, we see anhydrite sitting in its most intense volumes directly above the water table, with less occurring higher in the capillary zone. We'll address that question as we develop our notions of prograde versus retrograde salt distributions and their preservation in a coastal sabkha. Let's remind ourselves of some other physical processes that are happening. This is that image of the Abu Dhabi sabkhas. It's a 20-kilometre scale bar. On I've now put predominant wind directions of the shamal. These come from wave tracking offshore Qatar, but this is true across the whole of the Arabian or the Persian Gulf. This is a paper by Ubu Bakr and others. We can see that the shamal winds are persistent, hot, dry, northwesterly winds that blow across the whole of the Arabian Peninsula, including the UAE, and that they are quite active both during the summer and during the winter, with a very strong orientation. They're most persistent and severe in the summer. They're characterized by relatively high wind speeds, often reaching gale force, and they're associated with dust storms across much of the Arabian Peninsula. They can also, because of that intensity, disrupt daily life and transport and potentially impact the health of coastal populations. Often before a shamal blows through, the population's warned to stay indoors, shut all their windows, keep that dust out of the house. In terms of the Abu Dhabi sabkha, the thing to note is the positioning of that coastal zone where we see well-developed sabkhas with respect to those northwesterly shamal winds. The shamals supply much of the lagoonal sediment, the onshore matrix transport of lagoonal sediment into the Abu Dhabi sabkha. Most of the carbonate sediment, both the muds and also the coarser sediment, is transported into the supratidal matrix by the action of strong onshore winds, especially if we have a coincidence with high spring tides and an intense shamal. We drive both brine sheets from the lagoon and also sediment from the lagoon carried with those brine sheets across most of the sabkha surface. Historically, because their effects are so obvious on the sabkha, most workers assume that the shamals were the main drivers not just of sediment transport, but also of brine moving into the sabkha, which gave a predominance to the model known as the per descendum model for evaporite distributions in the Abu Dhabi sabkhas. The shamal's obvious influence across that coastal sabkha led to this notion that the brine sheets were the main suppliers of solutes into the capillary evaporites of the coastal sabkhas. This chapter will show you that's not the case. Much of the solute content is actually coming from resurging continental waters below the sabkha. They're carried there from the highlands, from the hinterlands, by the presence of that underlying continental dune sheet that underlies much of the coastal sabkha. The map on the left is showing the distribution of the dune sands across that section. The greys are indicating the sabkha plain. Then further out, beyond the carbonates of the southern margin of the Arabian Gulf, we have the marls of the Iranian Trough in that foreland basin, asymmetric basin, with a steeply sloping northeasterly margin and a gently sloping, Epiric-like southern margin to the Arabian Gulf. But the key thing here is that we have this aquifer system made up of these Pleistocene dunes underlying the whole of the sabkha succession. That aquifer system has a very strong influence on groundwater supply long-term into the coastal sabkhas across the region, through the UAE into Saudi Arabia. So we have the general models. This is the models that were put forward by Butler back in 1969 as part of the Imperial College Group, and also by Judy Mackenzie and others in the mid-80s, where we have the per descendum model for the supply of much of the solutes into the sabkha, where we have periodic washover coming from the lagoon during shamal recharge, moving those brine sheets and those marine-derived pore fluids into the sabkha and recharging hypersaline waters in the water table and returning them back up via a process of capillary evaporation. There's a time that was recognised by Mackenzie and others that we have little or no marine transport into the system, and we have a continentally derived transport of brines and a resurgence or a return of those brines through the capillary zone into the sabkha succession. Mackenzie and others, and also Muller and others, define that continental evaporation recharge style into the sabkha, and they divided the sabkha into three parts: the marine portion, the coastal sabkha portion, and the continental supplied portion. This is the basis for that subdivision, utilising the strontium ratios in work done by Muller, published back in 1990. We can think of the potential supply of brines into a sabkha as a per descendum model, indicated in that upper left diagram, where the bulk of the supply of sediment and also the solute is coming from the marine side of the system, washing up during shamals, especially if they coincide with high spring tides, on its brine sheets across the sabkha. Then we have the other end of that spectrum with the ascending brine model, where we have continental brines moving from the hinterland through that Pleistocene dune aquifer and then ascending through the Sabkha succession. We also have an evaporative pumping model that's lost much of its popularity. You can read about it in my book if you want to have more detail on that one, but I want to contrast the per descendum and the per ascendum hydrologies, which are the more realistic hydrologies operational within the Sabkha succession. That was the state of understanding in the 90s, but in the late 90s and the early 2000s, there was some groundbreaking work done by the USGS, especially by Warren Wood and others, where they established a series of wells, both deep and shallow wells, looking at the hydrology of the coastal sabkhas of the UAE. And they come up with some rather interesting conclusions. Here's two of them. The earlier conceptual model of evaporative pumping is not consistent with the fluxes in the measured hydrologic budget. Seawater flooding reflux model, which was the dominant model tied to the supply of both brine and sediment from the Shamal, is not consistent with the results of their work in that the hydrologic or the solute budget cannot be accounted for without seawater flooding and a resurgence of underlying groundwaters. Here is the area that they work. This is the Al-Taf, or the Trucial coastal zone of the Emirates. We've gone through the detail of this in the previous chapter, looking at the vertical sequence and the sedimentology of this system. Now we're going to look at the hydrology and the hydrologic budget. This is the piezometer nests that they established across the whole of that coastal zone in the UAE. And they also had a number of drill holes. There's something like 450 shallow piezometer nests they monitored across the Sabkha. And they also drilled a sequence of 6 deeper wells down into the tertiary succession. Here are the deeper wells that they completed in the tertiary formations. And notice also the positions of Site 1 and Site 2, which were meteorological stations that were tied back to those deep wells at Site 1 and Site 2. Also, there's a profile X prime, just to show you the detail in which they studied these successions, with piezometer nests drilled to varying depths across the Sabkha succession down into the underlying aeolian sands, these late Pleistocene sand sheets. Here's the results of the pore fluids established across that transect, going from the more continent-influenced superficial waters into the Sabkha waters with distance from the coast. The shore zone edge, or the Evans line edge, is around 12 to 16 kilometres from the shoreline position. Across the board, in all of those wells, we're looking at what are sodium chloride-dominated brines. When they concentrate, these brines will precipitate sodium chloride. But they also have significant volumes of calcium and sulfate in the range of 1,000 to 10,000 ppm. These brines are also capable of precipitating calcium sulfate, either as gypsum or as anhydrite. We'll come back to this chemistry shortly. Let's have a look at the evaporation rate. This is work done at the meteorological sites, Site 1 and Site 2, looking at measured Sabkha evaporation rates in millimetres per day across a 24-hour period, going from morning 8 a.m. through until 8 a.m. the following day. At Site 1 in September 97, the red line, we had significant evaporation throughout the day, but at night it fell off to where it became negative. We had dew points reached in the Sabkha overnight, so we had the reprecipitation of moisture on the Sabkha. Likewise at Site 2, similar profiles, but a greater moisture content coming out of those brines at night due to dew point, or those atmospheric systems at night with the dew point exceeded, so we get a negative evaporation rate. In the day, we had evaporation rates consistently above zero, and in the hotter portions, consistently above 1 to 1.5 millimetres per day. There's another interesting observation made at those meteorological sites. Here is Site 2 on Sabkha-Mati, where there was a rainstorm. After that rainfall associated with those rainstorms, you can see the greys are indicating the precipitation rates in millimetres, the scale on the right-hand side of that diagram, and the depth of the water table on the left. You can see rainwater recharge into the water table of Sabkha-Mati. The other thing they did, and this is the most significant observation that they made in terms of the precipitation of anhydrite, which is a retrograde salt, is they looked at temperature profiles in the Sabkha. Now, there are two scales here. There's the surface temperature scale on the right-hand side of that diagram, and then there's the subsurface temperature scale on the left-hand side of the diagram. The surface temperature scale runs from 25 to 55 degrees. The subsurface temperature scale, much narrower, runs from 34 to 38 degrees. First of all, this is time in a 24-hour period looking at the surface temperatures, and you can see there is a transition from temperatures in the mid to upper 20s in the cool of the early morning through to temperatures in excess of 50 degrees in the hotter parts of the day in the afternoon between 2 and 4 p.m. Then with nightfall, cooling back. So those surface temperatures fluctuate on the order of 25 degrees on a diurnal cycle on the surface of the sabkha. But there's a significant difference when we go below the surface. So that brown line, now we're looking at the temperature scale on the left-hand side of that diagram, at a depth of 1.52 meters is below the water table, and you can see it's a pretty constant temperature of around 34.5 degrees centigrade. If we look at the shallowest profile in those barometer nests, you can see that at 15 centimeters, 0.152 meters below the surface, we see a fluctuation, now a much smaller magnitude than we saw at the surface, but we're ranging from lows of a reorder of 36.5 degrees centigrade with highs getting up to 38 degrees centigrade. So we see a diurnal transition in those temperatures in the upper 15 centimeters of the sabkha sediments. We go a little deeper, we still see that diurnal transition, but it's much more reduced and it's delayed with respect to the peak and the trough. By the time we get to 60 centimeters below the surface, so we're now getting around the typical water table depth, there's a constant temperature of around 36 degrees over that 24-hour period, slightly lower in the latter part of that period, but pretty much hovering around 36 degrees centigrade. This introduces the notion that are these nodules that we see developing in the sabkha immediately above the water table an indication of temperature transitions rather than concentration in those pore fluids. This is what we see in the pore fluids in the Abu Dhabi sabkha. These are calculations from Warren Wood and others in a paper in Chemical Geology in 2005, where the temperatures are less than about 30 degrees. We are looking at chemistries undersaturated with respect to anhydrite. But once we reach temperatures, remember this is a retrograde salt, once we reach temperatures in excess of 30, 34, anhydrite is coming out of solution. It's precipitating. That 34 degree mark, if you remember back to the previous chart, was at around the water table. So in that transition from below 34 degrees to above 34 degrees, we have this transition where we go from undersaturated with respect to anhydrite to supersaturated with respect to anhydrite. Wood and others concluded nodular anhydrite is a thermalite salt. It is not an evaporative salt in the sense that we're seeing evaporation controlling precipitation. It's evaporatic in the sense that capillary wicking is controlling the upward movement of that water, but the actual precipitation process is not one of brine concentration. The precipitative process driving the precipitation of the anhydrite is one of heating of that brine, moving it from the undersaturated conditions below the water table into the warmer, saturated conditions for anhydrite above the water table. Wood and others also used that set of lysometers across the whole of that UAE coastal zone to calculate a hydrological budget. If you want the details on the hydrological budget, I'd recommend that you go back to the original papers or you have a look in the appropriate chapters in my book where we've discussed the work of Wood in a lot more detail. They took a volume of sabkha and calculated a solute load versus hydrologic load exchange volume in the sabkha. The left-hand diagram showing you that block of sediment, which is a meter across and 10 meters tall and 10 kilometers deep for their solute budget. We have the processes of recharge, superficial recharge, and that's a combination of chamal-driven brine sheets and rainfall versus capillary wicking and evaporation. They also discussed lateral inflow coming by continental resurgence of groundwaters coming off the hinterland and then lateral flow of those same waters out into the Arabian Gulf, and the potential for upward leakage, water rising by capillary wicking by resurgence of continental waters from depth. They divided their budget into two parts, into the water volume of the water budget and the solute flux within that water volume. They found that in terms of recharge in that volume of sediment, that 1 meter by 10 meter by 10 kilometer volume of sediment, there's something like 640 cubic meters of recharge water, evaporation's driving a loss of 690 cubic meters within that volume, and that we have a upward leakage volume of 45 cubic meters. There is significant flux of water through the sabkha in that combined process that we can observe at the surface of evaporation and recharge. Brine sheet recharge off the Gulf and rainfall recharge in the occasional storm. But in terms of the solute flux now, in terms of what's being carried in that flux, most of the solute content is coming not from that cycling of the coastal waters in the uppermost portion of the sabkha. It's coming from deeply supplied, resurging continental groundwaters rising through that sabkha, driven by the process of capillary wicking. Now we have to consider here how much solute load remains behind in the sabkha, not just the volume. And so the solute load remaining behind in the sabkha is mostly sourced in that upwelling from that regional groundwater resurgence, and the precipitation process of the anhydrite is driven by that thermolytic process, by the fact that anhydrite is a retrograde salt, and we see the bulk of the anhydrite accumulating across all the sabkhas in the UAE in that zone immediately above the water table. So if we come back to this notion of where does the anhydrite sit within the Abu Dhabi sabkha, it's not sitting directly below the sabkha Stokes surface, it's sitting directly above the water table. Coming back to this notion of why is there so much anhydrite immediately above the water table and not immediately below the Stokes surface, we now know the answer. It's because sabkha anhydrite is a retrograde salt, and it precipitates as we passage out of that zone below the water table into a zone where that brine is being heated as a capillary wicks in the overlying zone, and anhydrite drops out of solution. Now that contrasts to what happens to our prograde salts. So I'll just throw this slide in to remind ourselves of what we saw happening in Owens Lake, where in the upper 10 centimeters or so, we had the maximum change in the volumetric content and the maximum change in the chloride concentration in this zone of capillary wicking, both in the sandy mudflat and in the clay-dominant mudflat. So it's the heating of the pore waters that's moving liquid water into vapor in that uppermost 10 centimeters. This is typical evaporative solar-driven concentration, creating the precipitation of halite in that uppermost part of the column. But the precipitation of anhydrite is driven by the heating of that water, driven by that passage from groundwater, resurging continental groundwater, carrying the majority of the solute content up into the overlying succession above the water table as it heats. So then the question becomes, where's all the halite? Why haven't we seen a lot of halite remaining in the sabkha? We certainly see halite crusts, but they get flushed away. They get flushed away as the brine sheets flood the sabkha, or as rainfall floods the sabkha and we get a return flow and a loss of halite coming over that sabkha. There's another very interesting process that Steve Lockyer documented in a video, where this is taken from a tidal channel. And looking down on that tidal channel, you can see there's a two-way flow. You see the marine-induced onshore flow of water, and below that we have simultaneously a dense brine moving in the opposite direction, as you can see by that partially eroded section of algally bound material moving in the opposite direction. Now this is a constant diurnal mechanism where we're taking dense brine off the sabkha. At the same time, we're flooding the sabkha with less dense water. So this process is going to affect mostly the uppermost portion of the sabkha, which is where our halite would reside if it remained within the sabkha. But of course, what's happening here, well, this is a very obvious diurnal hydrologic mechanism here, is that along with the occasional rainfall flushing, this mechanism of moving undersaturated marine lagoonal waters across the sabkha, periodically driven by the shamal, is flushing the halite out of the upper section of the sabkha. But deeper in the sabkha, we see this nearer to the water table source, which is much less subject to this superficial flushing of brine. We see the anhydrite remaining behind in the sabkha. So this is a decoupled hydrology that we're seeing in the sabkha, and this decoupled hydrology characterizes most capillary evaporation zones. And have a look at chapter 2 in the book. You'll get more discussion of this in a whole series of hydrologic studies done in saline lakes in Australia and elsewhere, and the work of Tyler and others showing you this decoupling of the sabkha hydrology and the associated differential preservation of those successions as we compare the halite flushing with the more permanence of the anhydrite above the water table. Going back to what we started off this discussion of sabkha with, we said that sabkhas are edge indicators. We also saw that sabkha succession is unlikely to be preserved if that brine sump hydrology is transgressive. We also saw that we're not going to have good preservation if that upper section is in a prograding detrital sequence, be it carbonate matrix or siliciclastic matrix, because the water table deepens toward the hinterland, and so we get deeper erosion on the Stokes surface on the backside of the sabkha. Prograding sabkhas tend to be self-cannibalizing on their continental side. If we're going to preserve a sabkha succession, then we're going to have some sort of transgressive brining upwards and spreading laterally hydrology, where that sabkha succession is sinking into a calcium sulfate saturated brine below the water table. What does this mean in terms of the hydrology that is controlling the mineral distribution and the sediment distribution in our sabkha? Well, the sabkha succession, by definition, the evaporites in that sabkha are controlled by the various processes tied to capillary evaporation. They're going to occur beneath a capping deflation surface or Stokes surface. Within that column, if we use the UAE as an analog, we'll see gypsum below the water table and variable levels of gypsum and thermolytic anhydrite above the water table, tying back to the notion that the distribution of the anhydrite above the water table, not below the Stokes surface, is indicative of its retrograde or thermolytic origin. And if we look at the distribution of the anhydrite directly above the water table and halite, which forms ephemeral crusts at the Stokes surface, their positions are tied to their retrograde and prograde distinctions within that capillary evaporite hydrology. The preservation potential of a UAE-style sabkha is limited by deflation-controlled depth to water table, which is cutting deeper down into the sabkha on the backside of our prograding sabkha. The other limitation here is that gypsum in a modern sabkha is stable below the water table, but anhydrite is not. So the anhydrite that we form in the capillary evaporites, if we bury it into that succession, is going to reconvert to gypsum, which is problematic in terms of nodular anhydrite indicating a sabkha succession. If we want to preserve stacked sabkha cycles with Stokes cap capillary evaporite units, we're going to have a system that hydrologically is subject to rapid aggradation and subsidence into saturated phreatic zones with respect to calcium sulfate. This is a real limitation of the sabkha model. Think about it. Most of our ancient, well-preserved nodular anhydrite units can't have formed in a sabkha. We don't see the Stokes surfaces. We don't set up a hydrology where typical sabkha units will subside into a stable brine reflux curtain. Sabkhas don't tend to have the required scale or the brine supply volumes coming from the marine side inherent to a massive marine-fed mega-evaporite or mega-sulfate hydrology. Most of our ancient, thick, well-preserved nodular anhydrite units were deposited originally as either subaqueous gypsum or subaqueous anhydrite, not thin, stacked, Stokes surface-capped capillary evaporites.